Hi everybody, welcome to another video in differential equation, section 6.2, homogeneous linear equation with constant coefficient. So we're going to have the homogeneous equation, that means equal to 0. And this is a linear equation because all the derivatives and the function just raised to the first power. All the coefficients in this case are constant. So this is just like the linear equation that we have in chapter 4, except in chapter 4 we only have equation of order 2. This we have the order n. So whether we can write like that, or we can write as a linear operator equal to 0, it doesn't matter. But similar to what we have in chapter 4, it's similar to chapter 4, the solution will take the form of e to the rx, where r is the solution of the auxiliary equation. So we still have auxiliary equation, but this time it will have a higher degree because we have the higher order of derivative. Right, and then the three cases. This is exactly right what we have in chapter 4, where we have distinct real root. That's what we have, where we have the repeated root. To make them linearly independent, we have to attach the x into it until, so we have all of them will be linearly independent. Complex root in the form of alpha plus beta I, the solution is this. So that's exactly like what we have in chapter 4. Now, I would just want to prove the case B3, the case where we have the complex root. So when we have the complex root, the solution, if we assume that in this form, the solution will be in this form. Now, since those two are linearly independent solution, I can write as the linear combination. Right. Now what we don't particularly have is that the Euler formula, this, because it's one of the more common, but because we haven't learned that yet, but this identity e to the ix is equal to cosine of x plus I sin x. So when we have this, bring the real part and the imaginary part. This, we use that formula for this term and for this term. So we have that. Now, cosine is an even function. Cosine of negative is the same thing as cosine of positive. Sine of negative is, sine is an odd function, so now sine of a negative is a negative sign. Right? Multiply this out, combine the real parts and then the imaginary parts together, and you end up with this one. Now you can call this as a constant and call this as a constant with I. So we have the solution as e to alpha x cosine beta x, and then e alpha x sine beta x. Of course, this is exactly like in chapter 4. Yeah. So when we have this solution, we can write the solution as this. So those are two linearly independent solutions. So simple enough, right? Now we're going to solve this linear equation of the high order. Of course, the first thing we do is convert this equation into auxiliary equation. So from that one we have auxiliary equation. The fourth order derivative, you can write that as r to the fourth power minus r cubed minus 3r squared plus 5r minus 2 equal to 0. Right? The n order go to n power. The function has no power. I mean the function has no derivative, so it has no power. So that's just 2. Right. Now we just solve this equation. Right. The problem is this is the fourth order polynomial. There's a formula for it, but we haven't learned that yet. But it's not worth memorizing. Right. But so usually if we have the higher order than 2, recommend that you can use a calculator to get a head start. So x to the fourth minus x cubed minus 3r x squared plus 5x and minus 2. We see the graph. And look like there are two solutions. One of them is clearly -2. The other one look like it's 1. Right? Now, the difference of those two solutions is that you see that's -2. It goes straight through it. But when they go to 1, it's not going straight. It's kind of flat. But still going through it. Now we will go way back to coarse algebra. We learned that if it is an odd multiplicity, it will go through it. If it is an even multiplicity, it will bounce. So like for example, x squared equal to 0. Right? So even multiplicity, it will bounce. Thus the x-axis and turn around. If it is an odd multiplicity, it will go through it. Furthermore, the higher multiplicity, higher than 1 or maybe 2, 3 or higher, it tend to be flat. So because it is flat at 1, so we know that it is multiplicity of higher order here. It's multiplicity of 1 could be, multiplicity of this 0 could be 3 or 5, or we know it's odd because it's go through it. But because it's flat, it have to be more than 1. Alright, now, okay, so that's good. We know x is equal to -2 as a solution, x equal to 1. How do we find the rest? Well, if we know a solution, we know that we can factor it as r minus a solution. We know 1 is a solution. We can write r minus 1 as a factor. And then we can write r minus -2 because we also have -2 as the solution. And then we can determine the remaining factor. Right. The way we do this back in coarse algebra is we use what we call the synthetic division. If we know a solution, or if we can test a solution, looking for the ruler here. Okay. So, synthetic division, I will take out all the coefficients 1, -1, -3, 5, and -2. So, I will do that over here. Yeah, I just want to write that. Don't need the ruler. So, coefficient is 1, -1, -3, 5, and 2. And then first, from the graph that we have over there, we have x is equal to 2 and x equal to -1, right? So from graph, we have x equal to -2 and x equal to 1, and x equal to 1 possibly higher multiplicity. Right, first let's use the -2 first, because we know for sure it is a solution of -2. Now, synthetic division. Right, synthetic division. Now we write the coefficient, and then we write suspect 0. We don't know if it works or not, if this is a solution or not, but we just want to divide by -2 because that's what we have. Now first we're going to write this number down. So we're going to have 1. And then multiply. -2 times 1 is -2. Put in the next column. And then add them. -3. Multiply. Put in the next column. And then add. Multiply. Put in the next column. And then add. Multiply. Put in the next column. Yeah, I copied wrong. It should be -2. Multiply, add, put in the next column, and then add. if this is a 0, that means this is a 0. So this is a solution. Right. Now we can ignore the 0 there. We can work with the remaining. So with this we can say, if we want to factor, this one is factored as r minus negative 2, and then the remaining factor will be r cubed minus 3r plus 3r squared plus 3r minus 1. Yeah, I'm just going to use that as a coefficient of the remainder. Of course, the 0 is the remainder. We're not going to write that. Right? So from that problem, if we know a solution, we can factor that down into the qubit. Now we're down to a qubit equation. Now let's divide by 1. Because we suspect 1 is a solution, right? So once again, synthetic division, write down the first number, multiply, put in the next column, and then add. Multiply, put in the next column, and then add. Multiply, put in the next column, and then add. Once again, we have a 0 remainder. That should be 1. So if we continue with our factor, will be r minus 2, so r plus 2, and then we have r minus 1. The remaining factor will be r squared minus 2r plus 1. Right? So just if it is a 0 remainder, then it is a factor, and it is a Lewis number 0. Right? Now, because we suspect that 1 is a multiple root, so we might continue divide by 1 if you want to. By the way, if we have this, we can use quadratic formula factoring to solve for that, but I'm keep rolling with the synthetic division. I put the 1 down, write down the 1, multiply, put in the next column, and then add. Multiply, put in the next column, and then add. Once again, we have 0 as the remainder. So that means this is a 0 as well. And so if we want to continue, we have r plus 2, r minus 1, and then another r minus 1. What left is r minus 1. Yeah, so we can just factor. Of course, we can just keep divide by 1, but as when we have here, this is correct, corresponding to r minus 1 equal to 0. So we have r equal to 0. I mean r equal to 1. So the bottom line is we have r equal to 1 is a triple root. Right? If we look at the graph, it will flat at negative 1. Yeah. At 1, it go through it, so it is an odd multiplicity, and it's flat, so that will be a higher multiplicity. So bottom line is we solve for it, and we have solve this equation. We have r1 is equal to negative 2, and r equal to 1 is the triple root, so we can say 2, 3, and 4. Those are the triple root. From that equation, we have those solutions. And then we can write the solution. So y1 is e to the 2. We didn't have any variable here. It could be independent variable. Could be x, could be r, but could be x, could be t. Let's use t, doesn't matter. y2 e to the 1t or e to the t. But since it is the repeated root, y3 we have to multiply t to it to make it linearly independent, and y4 we multiply t squared to make it linearly independent. So because of the triple root here, we have the solution in this set. Multiply t and t squared to make it linearly independent, and because of that the general solution, linear combination of those linearly independent solutions so we have C1 e to the 2t, C2 e to the t, C3 t e to the t, and C4 t squared e to the t. Yeah. So just like what we have in chapter 4, except this time we have the higher order of derivative, which is the higher degree of a polynomial. We can solve it. That's perfectly fine. Now, the nice thing about this, what we learned in this chapter 6 is that we can write a derivative as the operator. So d square is like that. So if we want to, we can multiply this out. But in terms of auxiliary equation, even more direct, we just replace d by r, and we good to go pretty much. So this is the linear equation of order whatever it is, it doesn't matter, but we can just write the auxiliary equation. Just replace d by r. Yeah, so that's the nice thing about this. If we're not sure, we can always multiply it out. D square plus 1 square, d square plus 1 square, d square plus 1 times d square plus 1, d to the 4th plus 2d square plus 1 y, and yeah, we can just use that for the 4th degree. But just go ahead, and if there's the equation given in the form of d, replace d by r, and there is our auxiliary equation. So that's pretty simple there, right? Now, of course, from this one, if we need to solve for it, we take the square root on both sides. When we do that, there's a plus or minus here. So I have r squared plus 1 equal to. So notice that there's a plus or minus, so this is the double root. So there's two. One of them is plus square root of 0, one of them is minus square root of 0. So that is a double root. So here we have r squared equal to 1, negative 1, which is double. And here we take the square root on both sides again. We have r equal to plus or minus I. And that is a double root. What does that mean? Right. So meaning that we have r12 is equal to I and r34. Right, let's say r13 is I, and r24 is negative I. Yeah. So if I is a double root, negative I is the double root. Together, double and double, that's four root. So we have like that. Right. Because of the square here, when we take the square root, that is, we lose one of the multiplicity. So what we have here, we pretty much, we have r squared plus 1 equal to 0, and r squared plus 1 equal to 0, because we have the square. So we have that equal to 0 or that equal to 0, meaning that either one of them is equal to 0. So what solution we have is going to be repeated that again. So we have repeated root from one of them, and one of them has plus or minus I, so we repeat that again. We have the solution. So bottom line, we will have, right, by the way, if it's I, we can write this as a complex number. Zero plus or minus 1i. So we just write like that, so it is easier to write the solution. E to the alpha x and then cosine beta x. So in this case, beta is equal to 1 and alpha is equal to 0. So the solution, y1 is going to be e to the alpha x cosine beta x. Or because alpha 0, e to 0 power is 1 and beta is 1, so we just have cosine x. Y2 will be similarly will be e to the 0x and sine x, so that's just sine x. Now because they repeated, so R3 will be just exactly this cosine x, but we have to make them linearly independent, so we multiply an x into it to make it linearly independent. And same thing with y4, instead of sine x we have to multiply by x to it. So y1, y2, y3 and y4, so we have 4 solutions here, and the linear combination of them is the solution. So I'm running out of space, but we have those solutions. Let's just write here y equal to c1 cosine, c2 sine, c3 x cosine x, and then c4 x sine x. Yeah, so that is the solution to this problem, right? So if we are given the form in the operator, differential operator, is even better. Just replace that with r and just keep going from there. Similarly on this one, the auxiliary equation is r squared r minus 1 square equal to 0. So of course we have r square equal to 0 or r minus 1 equal to 0. So because we have r square equal to 0, this is multiplicity of 2. We have 1 and 2 be 0. And here we have r equal to 1. It's multiplicity of 2, so let's say 3 and 4, right? Because this is multiplicity of 2, so whatever we have is going to be 2 covers 2. Right, so R1, 2, R3, 4. Now just write the solution. Y1 is e to the 0 power of, we can use t or x, it doesn't matter. Let's use t here. E to 0 power is 1, so E1 is 1. Y2, we want Y2 to be linearly independent to Y1, so we will stick a t to it, and this end up with t. Y3 is e to the 1t or e to the t, and Y4, just to make it linearly independent, we stick a t to it. So those are the 4 solutions, linearly independent together. And then we can write the solution as y equal to c1 y1, c2 y2, c3 y3, and c4 y4. Of course, c1 times 1 is just c1. So that's what we have. So it's just more general than what we have in chapter 4. If we have the repeated root, just multiply t or multiply by x to make it linearly independent. If they're more than double root, multiply an extra t square and then higher order if we need to. But I said that's just like what we have in chapter 4. Now, let's solve the initial value problem. Meaning that after we find a general solution, we solve for the constant. But first, this equation, we have the auxiliary equation. Third derivative, r cubed plus 7r squared plus 14r plus 8 equal to 0. Now, of course, anything higher than quadratic, I will just graph it and see the intersection. R cubed plus 7x squared plus 14x plus 8. Let's see a graph. Right, it looks like we have the solution here is 1, 2, 3, -4, -2, and -1. It looks like that, but we need to check in the synthetic vision to actually confirm that those are the solution. So we have 1, 7, 14, and 8. Now we have -4, -2, and -1. So let's just try with -4 first. Now divide them. Rub out the 1. So 1 times -4. 7 minus 4 is 3. -4 times 3 is -12. Put in the next column and then add, multiply that -8. That's 0. And we check. It is 0 remainder, so this is a 0, and that is the solution. Next we have -2 and -1, but we'll just keep dividing. Drop the first number, so we can multiply, put in the next column and add, multiply, put in the next column and add. So we have 1 and 1, which represent r plus 1 equal to 0. So we have r equal to -1. So once again, because this is 0, this is 0, so we have that. So 1, 2, 3, solution. So from here we have r1 equal to -4, r2 equal to -2, and r3 is -1. So we can have the solution y1 e to -4t, y2 e to -2t, and y3 e to -t. And because the linear combination of them is the solution. C1 y1, C2 y2, C3 y3. Right, so that is the general solution. What we have here is we have this initial condition. So when we have initial condition, we have to substitute and solve for the coefficient C1 and C2, C3. Right. So first, the function is equal to 1, meaning that this is equal to 1, where we put 0 in for t. So put 0 in for t, make that equal to 1. C1 e to the negative 4 times 0 plus C2 e to negative 2 times 0 plus C3 e to negative 0. E to 0 is 1. So we just have C1 plus C2 plus C3 equal to 1. Next, derivative is equal to negative 3. So we need to take derivative first. Derivative of this e to negative 4t, it just going to bring down to negative 4. So we have C1 negative 4 e to negative 4t, C2 negative 2 e to negative 2t, C3 negative 1 e to negative t. Now we make them equal to negative 3, where we put 0 for t. This is equal to negative 3 when we put 0 in for t. Yeah, I put a negative 2 in front, that look better. T equal to 0. Once again, e to the 0 power is 1. So we have negative 4c1, negative 2c2, negative c3 equal to negative 3. So that is the second equation. Now we have the third condition. The second derivative at 0 is 13. So we have the derivative here. So we take the second derivative. This gives us negative 4c1, and derivative of e to negative 4t is negative 4 e to negative 4t minus 2c2 e to negative 2t, derivative of that. And minus c3, derivative of that. So this gives us 16c1 e to negative 4t plus 4c2 e to the negative 2t plus c3 e to negative t. And the second derivative is equal to 13. So we have 16 c1 e to the negative 4 times 0. If we put in 0 in for t, that will equal to 13. Put 0 in for t, that will equal to 13. So we have 16. Once again, e to 0 power is 1. So we have 16c1 plus 4c2 plus c3 equal to 13. Right. Now we have 3 variables, c1, c2, c3, and 3 equations, which is good. 3 equations, 3 variables. That's fair game. So, and of course we can use elimination or substitution, do by hand, but later on I recommend that we use calculator for this problem. So we have the system equation. So we use the matrix to do this. So first, I will draw this in the magnetic matrix. The coefficient 1, 1, 1, go to 1, -4, -2, -1, -3, 16, 4, 1, and 13. Once we put in the calculator, we will do reduce row echelon form. If we can get this into an identity matrix on the left hand side, then what we have here will be the solution for C1, C2, C3. Right, of course later on it might not get the identity like this. When we go to chapter 9, this will be a little more complicated, but now just get used to how to use the calculator. So second matrix, and we go to edit. Under edit, let's put matrix 8, hit enter. Now we enter the matrix. This is 3 rows, 4 columns, 3 by 4. 1, 1, 1, 1. -4, -2, -1, and -3. 16, 4, 1, and 13. When we're done, just hit second mode to quick. Now if we want to recall the matrix, hit second matrix under names. If we enter, we'll recall the matrix, and that is the values we have, and that's so good. Now we apply the reduced row echelon form into it. So second matrix again, go to second tab, math, go way down to option B. Just hit enter. So we have reduced row echelon form. Now we apply this to the matrix A. So second matrix under names, hit A. Yeah, so we have those 1, -1, and 1. So those are the solution C1, C2, C3. Right. Now if you want to delete that matrix, just go to second plus, so that gives us the memory management. Go to memory management or delete, and we delete the matrix values. Matrix A, just hit delete. Now when hit second matrix, it's not there anymore. Right. Now if you use DI84, it will be even better. We just do everything in the home screen. So hit second matrix, reduce row echelon form. Now if when your calculator you hit alpha and zoom, the bottom menu pop up like that, that means we can just put the matrix directly. So we have the 3 rows, 4 column matrix, and click OK. Right, very important. In here, do not hit the enter until you're done. Use this instead. So 1, go to the next one, 1. Yeah, doing this, we can see everything in the home screen. Is less room for error. Also, we use the negative sign, don't use the subtract sign. (16, 4, 1, and 13). Of course, we can enter, when we enter the numbers, use this to navigate between the cells. When we're done, hit enter. That's what we have. Right, C1, C2, C3. So with that, we can say, so the solution is C1 e to the -4t, so e to the -4t minus e to the -2t and plus e to the -t. Right, so that's what we have. So just like what we have in chapter 4, except this, we have the higher order of derivative. With that, of course, the high degree of the polynomial. And of course, the initial value problem, everything will be the same. I stop the section here. As always, watching, and see you in another video in differential equations.